everybody at home? Can I get a thumbs up that you see the board and hear me okay? All right, guys, we are starting section 4. We're going to do a couple more sections in chapter 6, and then I'm actually going to skip one section to get to chapter 7, because chapter 7 is some really important stuff that you would need for calculus, and I would hate to not get to that. All right, so a couple more sections, and then we're in chapter 7. The rest of chapter 6, guys, I'm probably sure you're going to be thrilled to hear this. It's all about the graphs of the trigonometric functions and how we can transform them. All right, our book is very, very big on graphing by transformation. All right, so what I'm going to do today, I'm probably not going to get that far. I'm just going to end up probably showing you the graph of sine and cosine in their original form, get you used to maybe the graphing calculator, and then tomorrow we can start performing some of the transformations, okay? All right. Here we go. So guys, the 6 trigonometric functions are periodic functions. We've said this before. After so many units, after so many inputs, they start to repeat themselves. So after so many inputs go in, the same outputs start to come back out. And guys, if you think of this in a circular motion, once you make one complete rotation around the unit circle, and now you get to angles that are bigger than 2 pi radians, they're still landing in the same spot as the angles from 0 to 2 pi. So all the same x and y coordinates repeat. So that means all the same ratios start to come back out. All right? The period is the number of units it takes for the graph to repeat itself, or the number of units it takes for to create one cycle. One cycle is one period, okay? The amplitude of a function is half the distance between the maximum and minimum values, highest and lowest point of the function. So basically the amplitude is, if you pictured this midline, this horizontal line that cut your graph in half, the amplitude would be the distance from that line to the highest point, or then from that line to the lowest point. Did it go from this line 1 unit up? The amplitude is 1. Did it go from the midline and go 2 units up? Then the amplitude is 2. It's half the distance between the highest and lowest point overall. Okay, so guys, we're going to graph the sine function first. Now to graph the sine function, I've picked the easiest angles for us to plug in and get ratios out. Because remember, that's how a sine function works. You plug an angle in, we're going to get a ratio of those side lengths out. All right, so I've picked your quadrantal angles. So I'm going to use the unit circle to help me graph this. So I've picked all the angles to plug in that land on a quadrant line. So I've picked 0, pi over 2, pi, 3 pi over 2, 4 pi over 2, which is 2 pi. And then we'll go to 5 pi over 2, 6 pi over 2, which is 3 pi, 7 pi over 2, 8 pi over 2, which is 4 pi, and we'll just keep going around using all of our quadrantals. So we need our ordered pairs. This was the point 1, 0, 1 to the right, 0, 1, 1 up, negative 1, 0, left 1, and then 0, negative 1, 1 down. So those are the only ordered pairs we'll need to create the graph of this function in its easiest form. All right, so like I said, I have picked all of our quadrantals to plug in. So I've picked 1 pi over 2. Your second pi over 2 is actually pi, guys. That's where pi lands. Then your third 90-degree angle, your 3 pi over 2. Then we're going to plug in 4 pi over 2, which is really 2 pi, right? And that will be one complete rotation. I like to put it like this. So guys, you're just counting by pi's over 2. 1, 2, 3, 4, 5, 6, 7. So 6 makes 3 pi. 8 makes 4 pi. 10 makes 5 pi. And 12 makes 6 pi's. I just didn't put them in their reduced form so you guys could see that we are just counting by 1 pi over 2 as we go around. All right, and then this would be our negative pi, and this would be our negative 2 pi. Let's create some points and graph them as we go. So I got a label. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2, and 8 pi over 2. We're just counting by 1 pi over 2 as we go. That's our counting increment. Negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2, and negative 4 pi over 2. And if you guys can recognize, the x and y coordinates represent the sines and cosines. The biggest x or y value that lives on the unit circle is 1, because that's the biggest ratio we could get for the sine or cosine. So we're going to go from 1 to -1 on the y-axis. All right, here we go. Let's create the graph. So if I plug 0 radians into the sine function, the sine of 0 radians, this is where 0 radians lands. What is the y-coordinate at 0 radians? It's 0. So sine 0 is 0. So 0, 0 is a point on the sine graph. All right, now let's plug in pi over 2. The sine of pi over 2 radians, well, pi over 2 is right there. The y-coordinate is 1. So the sine of pi over 2 is 1. So now the point pi over 2, 1 is on the graph. And notice, the only way we could take these trig functions to the coordinate plane in a horizontal and vertical motion is by labeling them in radians, because that's a real number, right? It's the arc length and how many radiuses fit inside of it, just a ratio. I could not label this in degrees, because degrees is a degree. It's not an actual real number. All right, here we go. Now we plug in pi. The sine of pi radians, well, that's where pi lands. The y-coordinate is 0. So it's kind of like, oh, I went from 0 to 1, now I'm back to 0. Are they about to start repeating? Well, if it goes back up to 1, maybe we can see a pattern. Let's see if it starts repeating yet. All right, now we plug 3 pi over 2 in. The sine of 3 pi over 2 is right there. The y-coordinate is -1. So we ain't repeating yet. It's not creating a pattern. All right, now I plug in 2 pi. The sine of 2 pi is all the way back in the exact same spot that 0 radians landed in, and the y-coordinate is yet again 0. So the sine of 2 pi is 0. So now, right now, this is what our graph is looking like. And if you remember anything from other classes, that is a sine wave. That is one period, that is one cycle. I've made one complete rotation around the unit circle, and now guys, 5 pi over 2 is going to land in the exact same spot as 1 pi over 2. So the sine is going to be the exact same ratio for that different angle. So we should start to see it repeat. We have gone through one cycle, one period. Now we should just keep creating this exact sine wave over and over and over again. All right, let's do it faster this time. 5 pi over 2 is right there. The y-coordinate is 1. So the sine of 5 pi over 2 is 1. All right, 3 pi is the same as right there. That is 3 pi's. The y-coordinate is 0. My 7th 90-degree angle, my 7th pi over 2 is down here in the same spot as 3 pi over 2, and my y-coordinate is -1. So now I'm down here at -1 again. And then 4 pi, it's really my 8th pi over 2. It puts me in the exact same spot as 2 pi and 0, and my y-coordinate is 0. So yet again, I've created another sine wave, because from 2 pi to 4 pi, another 2 pi radians went by. So another cycle, another period has created yet another sine wave. And then guys, after that, it just keeps on going. It just keeps creating that same exact sine wave. All right, let's go backwards. If I plug in -pi over 2, guys, remember, negative angles of rotation, we rotate clockwise. So -pi over 2 is right there. It landed in the same spot as positive 3 pi over 2. The y-coordinate is -1. All right, -pi is right there. The y-coordinate is 0. All right, -3 pi over 2 is right there in the same spot as positive 1 pi over 2. The y-coordinate is 1. All right, and then -2 pi, it lands in the exact same spot as 0 or positive 2 pi radians. The y-coordinate is 0. And you can see you've created yet another sine wave from 0 to -2 pi, because every 2 pi radians creates one sine wave. That's the period. That's the number of units that have to be plugged in before the outputs start to repeat themselves. All right, so here we go. From 0 to 2 pi, that's one period, which is equal to one cycle, and that takes 2 pi radians to create. So one period or one cycle takes 2 pi radians. and then everything starts to repeat. Okay. So again, if this is my 8 pi over 2, 9 pi over 2 is 1, right? So 0, 1, 0, -1, and then 0. You shouldn't need to have to plug them in anymore. You should see the pattern of your outputs. Oh no. I want to fill all this in, but now I have to erase it. All right, well, let me do this first before this gets out of sight. All right, so now let's write down the important properties of the sine function. What is the domain of the sine function? What angles are you allowed to plug in and take the sine of? Guys, look at all the angles you've plugged in. Do you see a bad angle that you're not allowed to plug in and it's going to create some undefined ratio? No, all real angles. You can plug any angle you want in and you're going to be able to take the sine of it. That's the beauty of these angles of rotation. I can create an angle of any size and plug it into the sine function. All right, the range. Well, guys, look at the ratios. The ratios of an x-coordinate to a radius, or a y-coordinate to a radius, or the old school definitions, an opposite to a hypotenuse, an adjacent to a hypotenuse. The hypotenuse and the radius were always big, so it's always a small number divided by a big number, which keeps the ratio in between that 0 and 1 and that 0 and -1. The only ratios that can come out of the sine function are ratios in between 1 and -1. So your range is -1 to 1. Those are the only ratios that come out. All right, your period. Well, guys, what did we say it took? How many inputs have to go by to create one sine wave before those outputs start repeating themselves? 2 pi, right? One complete rotation around the circle, and now all the outputs come out again. So the period is 2 pi radians. And then the amplitude. Well, guys, the y-axis, the x-axis cuts this graph literally in half. So we think of the x-axis, the line y equals 0, as what we call the midline. It goes right through the middle of the graph. All right, and the amplitude is from that midline, how many units up did you go? And then from that midline, how many units down? It should be a positive value when we talk about it. I went from the midline, I went 1 unit up, or I went 1 unit down. Or think of it, the amplitude is half the distance between the highest and lowest point. So the highest point was at 1, the lowest point was at -1, that's 2 units of space. Cut that number in half, what's half of 2? It's 1. The amplitude is +1, and it should always be described as a positive number. So it's the absolute value of whatever number you get. All right, what else do I have down there? The x-intercepts. All right, the x-intercepts. Guys, take a look at this. Look at the x-intercepts. It crosses the x-axis here at 0, at pi, at 2 pi, at 3 pi, at 4 pi, at 5 pi, at 6 pi, at 7 pi. Can we sit here and literally count all the x-intercepts on this graph? No, they're infinite. It has infinitely many x-intercepts. We can describe them by saying the x-intercepts right now, it looks like they're happening at, what did we say? 0, and pi, and 2 pi, and 3 pi, right? So what we say is x will equal 0 radians is our first x-intercept, plus or minus. The next one is 1 pi away from that. The next one is 1 pi away from that. The next one is 1 pi away from that. So plus pi radians times k revolutions. How many units or how many intervals away are you going to go from there? We can also describe it, guys. They are integer multiples of pi. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Integer multiples of pi. Okay, what else? The y-intercept. Guys, where does the sine wave cross the y-axis when y is 0? So the y-intercept is 0. And that's actually how you're going to be able to tell the difference right away between a sine wave and a cosine wave. Because the cosine wave is actually just described as a transformation of the sine wave a few units back. I just always remember the sine curve always starts at 0. Sine 0, 0. You plug 0 in, 0 comes out. So the sine curve starts at 0. That's how you'll be able to tell the difference between cosine when you see his graph. His graph doesn't start at 0. All right? And then we asked for, all right, guys, this graph, if you remember the sine graph, it had symmetry to the origin, right? XY is on the graph, but so is the opposite of X, the opposite of Y, right? You plug the opposite of X in, the opposite of Y comes out. This is an odd function with symmetry to the origin. So that's what I was looking for on the next graph. On the next line, oh, I can't stand that I didn't move this up. I can't move the graph yet. I don't want to be able to describe questions. All right, then I'm going to say this. I'm going to write it in a second. Let me just talk about it. The 4 main subintervals. Guys, the quadrants, right? The coordinate plane was cut into quadrant 1, quadrant 2, quadrant 3, and quadrant 4. We do the exact same thing on the graph this way, except you're not looking at it in terms of a quadrant, right? Technically, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Don't think of it like that. Think of it right here. These subintervals from 0 to pi over 2, guys, those are your quadrant 1 angles. And then on this leg of the graph, those were your quadrant 1 ratios that would have come out, that would have lived on the unit circle. From pi over 2 to pi, that's quadrant 2 angles. That's our second subinterval, right? And then on this leg of the graph, those would have been your quadrant 2 ratios. And if you remember, the sine ratios are positive in quadrant 1 and quadrant 2. Hence why his graph is in the positive for quadrant 1 and quadrant 2 angles. From pi to 3 pi over 2, guys, that's quadrant 3. Those are quadrant 3 angles. And then this leg of the graph shows the quadrant 3 ratios. They're from 0 to -1. And then 3 pi over 2 to 2 pi, that's your quadrant 4 angles. So that's your 4th subinterval that we kind of cut this graph into. And then this leg of the graph shows your quadrant 4 ratios. They're going from -1 and then they're getting closer to 0 as the angles approach 2 pi radians. All right, and guys, then we're back to repeating. Now you're back to, these are quadrant 1 angles. These are quadrant 1 ratios. These are quadrant 2 angles. These are quadrant 2 ratios because the graph in the cycle has started to repeat. So that's what I'm looking to put on those lines. I'll write it in a second. And then your 5 key points. The 5 key points that we should use to create one cycle are 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. Those are the 5 key points that we definitely use to create one cycle of the sine wave. All right, let me move that up and I'll fill it in and we can move on. So if we start graphing using transformations, these key points are the points they want you to memorize and they want you to use them to transform them. Times the y's by 2, times the x's by -3. Do what you got to do to create the new ordered pairs on the new transformed graph. All right, our subintervals, they go from 0 to pi over 2, right? That's quadrant 1 angles. They go from pi over 2 to pi, those are our quadrant 2 angles, 90 to 180. And then we go from pi to 3 pi over 2, right? Those are our quadrant 3 angles. And then we go from 3 pi over 2 to 2 pi. Those are our quadrant 4 angles.
Is there anything that we could go on for the function with symmetry?
So this was an odd function with symmetry to the origin, right? The sine function was an odd function that had symmetry to the origin. Where's my good marker? All right, and then your key points were 0, 0, right? Sine 0 radians, the ratio was 0. Pi over 2, 1, the sine of pi over 2, the y coordinate was 1 there. Pi 0, 3 pi over 2, -1. And then we're back to 2 pi where we started at 0, and 0 comes back out. Those are the 5 key points that we use to create that first cycle. All right, sorry that I didn't put that on there. I wish I had moved that up. Okay, so that's how we graph the sine function. Then you have I say sinusoidal, it might be sinusoidal functions are transformations of the sine function. The cosine function's graph is actually a transformation of the sine function's graph. Watch, you'll see it. You'll see that each one of these trig functions actually lives on the other one's graph somewhere along their period, all right? So let's graph the cosine and see how we can find the sine curve on his graph.
Wait, don't erase the next yet.
Yep, let me just make sure. I'm showing everything. That's good. Oh, God. How do I only have 6 minutes left? Are we all right, Michael? They'll be on the filled in notes, Michael. I have to go to try and get this one, but they'll be on the filled in ones. All right, guys, let's graph cosine really, really quick. Let's use our unit circle. 1, 0, 0, 1. All right, here we go. Same thing. We're counting by pi's over 2. So 1 pi over 2, 2 pi over 2 is pi, 3 pi over 2, 4 pi over 2 is 2 pi, 5 pi over 2, 6 pi over 2 is 3 pi, 7 pi over 2, and then we have 8 pi over 2, which is our second complete rotation, which is 4 pi. Negative 1 pi over 2, negative 2 pi over 2 is negative pi, negative 3 pi over 2, and our negative 4th pi over 2 is just negative 2 pi. We're just counting by 1 pi over 2 as our counting increment. All right, here we go. 0 goes in. The cosine of 0 radians. Guys, at 0 radians, what's the x-coordinate? 1. So the cosine doesn't start at 0. It starts at a y-coordinate of 1. It starts up high. All right, then we go to pi over 2. The cosine of pi over 2, the x-coordinate is 0. All right, then we go to pi. The cosine of pi, the x-coordinate is negative 1. Oh. All right, now we're at 3 pi over 2. The x-coordinate of 3 pi over 2 is 0. And then 2 pi, we're right back to where we started. The cosine of 2 pi radians, the x-coordinate is 1. So guys, there it is. Now we're going to start rotating around again, and we're just going to land on all the same x and y coordinates. So one cosine curve looks like that. Now, I don't know if this helps you guys, but this always helped me. Do you remember when you were in elementary school and you would draw like a picture and you'd put your sun up in like the corner? Don't tell me you never did this. Everybody did this, all right? You know when you would draw your seagulls? Anyone ever draw a seagull like that? Yes? So seagulls are near the coast, right? So to me, this looks like one of my seagulls. Like it's up, like it looks like a seagull near the coast. So a cosine graph looks like our seagull. It starts up at 1. I don't know if it makes sense to anybody, but it made sense to me. And that's always how I remembered the cosine graph looks like that. It starts up at 1. It reminds me of my seagull near the coast. Cosine, if that helps anybody. All right, here we go. And then, guys, everything starts to repeat again. 5 pi over 2, we're back up there. That's 0. 3 pi, we're back over here. That's negative 1. 7 pi over 2, that's here. That's 0. All right, and then 4 pi, we're all the way around again at an x-coordinate of 1. And we've created yet another seagull, another cosine wave. All right, and then again, you would just rotate around again, get all the same outputs. If we go backwards, negative pi over 2 is 0. Negative pi is negative 1. Negative 3 pi over 2 is up here. That's 0. And then negative 2 pi is right there at 1. And you've created yet another cosine wave in reverse. Okay? But guys, if you look, if I went back to pi over 2 to 3 pi over 2, what wave is that? That's the sine wave. It's just shifted back 1 pi over 2. So the cosine is just a transformation of the sine's graph, they said. All right, but he goes from 0 to 2 pi. This is 1 period, which is 1 cycle, which is 2 pi radians. It takes 2 pi radians to create a cosine wave. All right, what's my time looking like? 2 minutes? All right, and again, here is your x-axis, cutting that graph in half. So the line y equals 0 is acting like that midline, right? So from that midline, my graph goes 1 unit up and 1 unit down. So that's my amplitude. My amplitude is 1 unit. All right, let's see if we can just fill a few of this information, and if I have to stop, I have to. I didn't create homework for tonight because I knew I wouldn't get to anything good information, so let's just see what we can fill in, and then tomorrow I'll try to get to some examples, and you'll have your first homework. All right, our domain. Guys, what angles can we plug in? Any angle we want. All real numbers. All real angles. My range. Only what ratios come out. Again, the ratios live in between 1 and -1. My period is 2 pi radians, and my amplitude is 1. Right? I went 1 up and 1 down from that midline. If I added this distance together from high to low, it's 2 units, cut it in half. It's 1 unit. All right, the x-intercepts, maybe that's where I'll have to stop. The x-intercepts, guys, look where it crosses the x-axis. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. The next one is 9 pi over 2. So it has infinitely many, but we can say the first one is at pi over 2, plus or minus. The next one, again, it's pi radians away, times k revolutions. Or we can say this time, 1 pi over 2, 3 pi over 2, 5 pi over 2, odd integer multiples of pi. Odd integer multiples of pi over 2, sorry. And then I'll stop there. All right, like I said, I knew I wouldn't get far, especially as far as questions go, so I didn't create a homework. I'm just trying to get you guys set up with the original graphs so we can move into the transformations. All right, I apologize if I went too fast at that point. Just these classes are not long enough. Are you guys okay? Everybody's good? And again, hopefully you've seen these graphs before, so it's nothing new. All right, enjoy your day. Everybody at home, enjoy your day. I will see you guys tomorrow, and we'll start back up again, all right? Bye, guys.